Thank you very much, Dieter, for the very nice introduction. So I'm very happy that I have the opportunity to present our study and also to be joined by Helge Schramm from Danfoss, who afterwards will give some insights into case studies of Danfoss. But now let's jump into this very interesting topic, and I think also the very interesting results of the study. First of all, I'd like to share with you briefly the storyline of the whole first 30 minutes. First of all, I'd like to give a brief context about the challenge that is posed by the EC roadmap on a low-carbon economy. And then, of course, the whole study also takes place in the context of the EC's 2016 winter package, which really can be seen as a milestone to face the challenge. Then we go to our study, Optimization of Technical Building Systems, and actually we use the picture of a sleeping giant and how to use him in this challenge. Then we will have a look at the status quo for the optimization of technical building systems and ask the question why this giant still sleeps. And then, of course, it's nice to know to get the insights from some calculations we did. So what could that giant do in typical existing buildings? And when extrapolating these insights from single buildings to the overall EU, we also asked the question what the giant could do in the EU building stock until 2030. And based on that, when we know about the potential, it's of course very interesting to think about and to give some policy recommendations on how to actually wake up the giant. So the EC roadmap, I will just briefly remind you to the very ambitious targets the EC roadmap to a low-carbon economy has set some years ago. You can see here on the left side the overall reduction target, greenhouse gas reduction, compared to 1990. It's 80% until 2050 in a cross-sectoral view for the overall EU economy. And then we have also the two sectors which are to provide the highest savings, which is the power sector, and of course, in the context of this session, the building sector. And you can see the building sector is to achieve or to reduce 37% of CO2 reductions until 2030 and even 88% reductions until 2050. But this is just valid for, let's say, a target, a climate global warming target for 2 degrees Celsius. But when looking at the recent agreement that we had in Paris at a conference of the parties, where the target was set to be, it should be well below 2 degrees Celsius. These targets get even more ambitious. So cross-sectoral, this would mean a reduction of minus 95%. And for the building sector, it's minus 53% until 2030 and minus 91% until 2050. And you can see this is really a very high ambition. And with a focus on our study, which was meant to have a view until 2030, the minus 53%, so the more short-term reductions were in the focus. So what did the winter package say? Of course, many of you probably know that the winter package did not just focus on buildings, but it also included other parts. But let's focus on buildings. So the winter package also includes the revision of the Energy Performance of Buildings Directive. And it says that its main objective is to accelerate the cost-effective renovation of existing buildings. So the update, which is currently under discussion of the EPBD, its main objective is to accelerate the cost-effective renovation of existing buildings. Please keep that in mind because this is the perfect background for the whole study. So this acceleration is urgently needed, as without there will be a big gap. The 30% energy efficiency target, which was also recently agreed on within the Commission, wouldn't be achieved, and also the greenhouse gas reduction target that I just presented to you, which are mentioned in the roadmap, they also would be clearly missed. So something needs to be done. So I was hinting at the sleeping giant, and this was the topic of our study, the potential of technical building systems. And in the center of the study, we had two questions. Question number one, how much can optimization of the energy use of technical building systems contribute to fill the gap that we will have without further action until 2030. And then the second question is, which policy measures should be taken to let optimization of TBS significantly help filling that gap until 2030? And the policy measures that we designed, they were also focusing on what could be done in the context of the update of the Energy Performance of Buildings Directive. So first of all, let's start with the basics. What are technical building systems? Here also the EPBD helps. There is an Article 2 with definitions. It includes several definitions, but also a definition for technical building systems. And this definition says technical building systems is technical equipment for the heating, cooling, ventilation, hot water, lighting, or for a combination thereof of a building or building unit. So you will see this is quite important also in the context of the Article 8 that we will see later. But you see it covers really the overall technical building systems that you usually have in a building to provide the energy services that we need to have a good life in our buildings. So, but what is the status quo? As you can imagine, we have done the study because we feel that there is still some potential. And the question is, why does the giant still sleep? So first of all, you could think maybe it's a lack of regulation, but in fact there is some regulation. I've listed the most important regulation in the EU briefly on this slide. Let's start with the EPBD. First of all, you have an Article 1 in the EPBD, which first of all mentions the application of minimum requirements to the energy performance of technical building systems whenever they are installed, replaced, or upgraded, which is important. It's already mentioned in Article 1, so not just in Article 8, which will be in the focus of our study later on. And then we have Article 2. I just showed it to you. It includes the definition for technical building system. Then we have the central article, Article 8, which is actually called Technical Building Systems. And this article sets system requirements for technical building systems which are installed in existing buildings. This is important. The focus of our study is on existing buildings. Then we also have Articles 14 and 15, which set requirements for the inspection of heating systems and air conditioning systems, obviously also a part of technical building systems. And furthermore, apart from the EPBD, we also have eco-design regulations, which, for example, set efficiency requirements for products like boilers and pumps. And we also have the Energy Labeling Directive. You all know the energy labels, which, for example, exist for space heaters, which also belong to the sphere of technical building systems. The central article that I mentioned was Article 8, and in order to emphasize its value, I have cited on this slide the most significant part of it, and I really would like to read it so you really get the context of the overall study. Article 8 says, member states shall, for the purpose of optimizing the energy use of technical building systems, set system requirements in respect of the overall energy performance, the proper installation and the appropriate dimensioning, adjustment and control of the technical building systems which are installed in existing buildings. Then it says member states may also apply these system requirements to new buildings. As I said, it's not the focus we have now. Let's focus on the existing buildings. And the next sentence is also very important. System requirements shall be set for new, replacement, and upgrading of technical building systems. And the system requirements must cover at least heating systems, hot water systems, air conditioning systems, large ventilation systems, or a combination of such systems. Maybe you remember the definition I just gave from Article 2. The difference is that in Article 8, lighting is not mentioned explicitly, but in our study we also included lighting, at least in one of the scenarios and options that we analyzed. You will see later. So, but what is the state? I mean, Article 8 is quite clear. It's requiring action on technical building systems, and I will briefly jump back. Whenever system requirements or systems are replaced, upgraded, or renewed. But the current status is that actually, rather than for all existing buildings, technical building system requirements are set only for new buildings or major renovations requiring a building permit in most of the EU member states at the moment. System performance only exists on an overall building level, so the overall building energy performance, rather than looking at the energy performance of the technical building system. In many member states, there are no system requirements at all, but rather requirements for individual elements. And some member states even link the optimization of technical building systems to the exchange of main parts, for example, and not for any change in the technical building systems. And you can also see these restrictions in some lists that member states have related to Article 8, which just cover individual measures like the exchange of a boiler and not really to the overall optimization of the total building system. So, but why do we have this state? So we also try to find out why it is like that. And we found that there is really a lack of awareness about the scope of Article 8, because Article 8 says that the systems have to be optimized whenever technical building systems in existing buildings are newly installed, replaced, or upgraded. So all the restrictions that I just showed you in the previous slide, in principle, they should not be the consequence of Article 8, but actually the scope should be much wider. So system requirements for the overall energy performance, this is also something where member states obviously have difficulties to determine this overall energy performance in existing buildings, because you can imagine in many cases there is no real documentation, and so you really would need to spend a bit more time in order to find out the overall system performance. But also as to setting system requirements in existing buildings, many member states obviously feel it's a bit too difficult to set such overall system requirements when just single components are exchanged. Furthermore, differentiation between system and component seems to be unclear. You can see that in many reports, for example, in the concerted action report, where systems are spoken of, but then in the next sentence already examples of components are given. Then in some member states, there is, of course, already regulation about technical building systems, which was in place before the EPBD came into force, and some of the member states judge this already to be sufficient and are a bit reluctant, we could say, to address the EPBD requirements in their regulations. Then we have the escape door of the technical and economical feasibility. So in some cases, this also may be used as an excuse for not really acting on Article 8. So now we looked at individual buildings, because in the end, when you want to know the potential for what you can achieve with the optimization of TBS, you would like to have some numbers, kilowatt hours, how much can you save? And for this purpose, we looked at different so-called reference buildings. So we had a look at residential buildings. We took the example of single-family homes with a gas boiler, and we also took the example of 3 different multi-family houses where the difference was that they had a gas boiler or a district heating connection or a heat pump. And in order to get a cross view about the total building stock, of course, we also looked at some typical non-residential buildings. We had a look at 2 variants of an office building, where one had a radiator heating and the other an air heating system. And then we also looked at supermarkets with and without heat recovery from refrigeration. for all these different reference buildings that I've just shown you, we usually looked at two different bundles of measures. The first bundle of measures we called the Get the Basics Right bundle, and the second bundle we called the High Performance bundle. In the Get the Basics Right bundle, we exactly included what the Article 8 of the EPBD requires, which is the appropriate dimensioning. For example, the sizing of pumps, the proper installation, for example, the insulation of pipes, and also system adjustments, which, for example, is aiming at hydronic balancing or installation of thermostatic radiator valves. On the contrary, the high performance measures, they included all the Get the Basics Right measures, and on top of that, they included automation, control, and monitoring, for example, the installation of electronic thermostatic valves. So for all the different buildings that I've shown you, residential building and non-residential building, we put together measures which made up, first of all, a Get the Basics Right bundle, and on the other hand, a high performance measures bundle. And then we calculated the savings these bundles would have in these different buildings. For each of these combinations, we generated fact sheets in order to show the savings potential. I don't want to go into the details here, but you can see the information which is usually provided on these fact sheets. You get a brief introduction into the geometry, for example, and the technical building systems which we considered in these reference buildings, which we selected to be, let's say, an average building of this type of buildings across Europe, to make it representative for the European building stock, because we are talking about existing buildings still. Then on these fact sheets you can see the savings compared to the status quo for both the Get the Basics Right and the high performance measures. So you can see it here, Get the Basics Right column, and then here the high performance column. And you will see the total savings of these bundles in terms of final energy. In this example, 20% savings from the Get the Basics Right package and 41% savings for the high performance package. And here at the bottom you can see for each of these reference buildings not just the final energy savings, but also energy cost savings, the investments related to that, and the payback periods following from the energy cost and the investment. So the summary about the savings potential in typical existing buildings is that single measures, they often are very easy to implement, and sometimes not just as part of a bundle, but also as standalone measure. And they usually have very short payback times of less than 5 years, and sometimes of much less than 5 years. But still, bundled measures, so bundles of measures, they are preferred because they create synergies and usually yield higher savings. And we found in the bundles that we calculated, and which are in line with the requirements of Article 8 EPBD, that on average up to 30% energy could be saved in each building, which is touched until 2030 and where technical building systems are renovated. So, but 30% just from the optimization of the technical building system. So when you extrapolate these savings that we calculated for these individual different buildings to the overall EU building stock, you have to make some more assumptions. Then you have to think about, okay, what renovation rate do we assume? And in this case, because there is no clear indication in the literature, and we assumed that the renovation would take place approximately at the same speed that we can observe for the exchange of boilers in buildings, which is approximately 3.6% per year. So we assumed that every time an element or a technical building system is renovated, that this happens at a renovation rate of 3.6% or at a rate of 3.6%. And every time the TBS is touched, Article 8 is actually implemented, either with a Get the Basics Right package in this building or with a high performance package in this building. So regardless what you do, the Get the Basics Right package or the High Performance package, both packages usually have very high savings. You can see that in some numbers that I will show you now. The potential energy cost savings, which build up until 2030, will be somewhere between 36 and 67 billion euro per year in 2030, And the payback, the typical payback of Get the Basics Right packages is 2 years. And also on EU level, the high performance package implemented as a scenario until 2030 would have an average payback of 5 years, which is still very short. So when we focus again on the CO2 emissions, which I was introducing you into when I showed you the savings ambition around the EU roadmap, then it's very nice to see what actual CO2 savings we could achieve with the optimization of technical building systems until 2030 within the EU 28. So when we calculated the scenarios until 2030, you can imagine that some of the measures, of course, would happen anyway as to optimization of technical building systems. And according to our calculation, from the optimization of technical building systems until 2030, a saving of approximately 30 megatons of CO2 would occur. But on top of that, with a proper implementation of the Get the Basics Right measures, an additional 61 megatons of CO2 could be achieved as a reduction per year in 2030. When we do the same for the high performance package, so when you imagine that in each renovation, so at a renovation rate of 3.6% per year, at each renovation the high performance package would be implemented, even an additional 126 megatons CO2 per year could be saved. And of course these numbers are a bit abstract, and therefore we added some further numbers in order to give you a bit of direction how much that is. So imagine that the total annual CO2 emission of Finland in 2014 is 61 megaton, which is equivalent to the amount of savings that you could achieve by just optimizing the technical building systems with the Get the Basics Right bundle. And in order to have a comparison for the 126, you see also the annual emission of Belgium and Slovakia, which is 156 megatons CO2 per year. And when you add up the high performance and the business as usual, which is the total emission saving that you get by technical building optimization, you really see the very high order of magnitude of these savings. So, and last but not least, because our context is the EPBD, it is interesting to see that the additional savings which are meant to be achieved with the proposed EPBD that was part of the winter package, it is only 38 megatons CO2 per year in 2030. So which is even less of what you could achieve by just implementing a Get the Basics Right package. Maybe some of you also know that in the discussion, in the impact assessment before the EPBD draft was published, also a mandatory renovation was under discussion. And in case the Commission would have followed this option, the calculated additional savings would have been 134 megatons of CO2. So just to give you an order of magnitude of the really very significant savings that can be achieved by optimizing technical building systems. So what findings do we have on the technical building system optimization? Obviously, we have a very vast but yet unexploited climate, energy, and cost benefit on EU level. And unfortunately, EPBD Article 8 does not deliver yet, and therefore a boost in the member states' compliance with Article 8 is really needed. Packages of measures are preferred, and there are some individual really no-brainer measures, short payback measures like thermostatic valves and hydronic balancing, which not just provide savings, but they also have co-benefits like they really care for the indoor air temperatures being close to users' needs. They have lower power consumption of circulators, lower water temperature in the heating circuits, less distribution losses, and a higher efficiency of heat generators, which adds up to the total saving impact that we calculated in the packages. So furthermore, you really have to be aware that because of the high renovation rate of 3.6%, which is much higher of the renovation rate of 1% for the total building stock, or 1.5, 1.4%, that you may have heard recently for the renovation rate, it's much faster, and therefore the renovation of technical building systems would deliver quick savings without creating lock-in effects, because it doesn't stop you from achieving further efficiency improvements. So because it's so quick, you can imagine that savings build up very quickly, and in the end, when talking about climate impact, the cumulated CO2 emissions are decisive, and therefore it's good to also have quick savings, but no regret quick savings which don't create lock-in effects. It's also good to think about TBS optimization because it improves the performance during stepwise renovation. It leads to better efficiency in stages towards NZEP where technical building systems may be oversized when you go step by step towards NZEP. It also serves for a better persistence of energy savings, so not just first year savings, but by also having better control, monitoring of the savings, you will also be better informed about the savings, and you can take action when something goes wrong. So then we have advanced building automation and control systems, which is, so to say, the advanced part of the technical building systems. They will help us to actually make technical building systems become an active, manageable part of the energy system, which we need in order to get more flexibility on the demand side. And last but not least, it's also important that, of course, technical building systems and their optimization is really important, but it's not the only thing that will help us to achieve the very ambitious targets that I just mentioned at the beginning, but it has to go together like twins with the improvement of the building envelopes. So what are the policy recommendations that we get out of that? The EPBD revision should actually push the rate and depth of technical building systems optimization in existing buildings, and therefore, from the examples I gave you, we think that more guidance should be provided on Article 8. For example, the EC could add best practice examples for the enforcement of its implementation, like, for example, the current German grants for optimization of heating systems. It also could link requirements to functionalities of TBS, which we didn't find in current member states legislation, to make it easier to understand what it is about. It is about the control of energy generation, distribution, and emission of heating and cooling, and when you link it to these functionalities of TBS, then it also might be easier to give guidance and to create an idea amongst the member states what actually the target of Article 8 is. Of course, it's not sufficient to just have something in Article 8, but you really need to push for implementation. And we think because of the very short payback times of TBS optimization, and because usually there are no regret options which don't stop you from doing further efficiency improvements afterwards. When you take the example of controls for room temperature, for example, in this case, you even could think about to make such measures mandatory in the member states and to also give a deadline for the actual implementation of such measures. And in this specific measure, controls for room temperature, we also think it's really a precondition for consumption-based billing, and that's why we gave this as a very example for a measure that even could be made mandatory. So then the EPBD also encourages member states to hand in national long-term renovation strategies, and if the Commission would ask or encourage the member states to clearly address the most efficient order of such measures, so rank the measures according to their economics, for example, then usually optimization of technical building systems would rank high. With a view to the growing together of the demand side and the supply side. We also think that building automation control systems will play a very strong role in the future, and therefore the EPBD revision also should provide further guidance on building automation control systems, meaning how could they be properly implemented, including best practice examples. It could give more guidance on cost-optimal solutions, which was not really included in the recent round of cost optimality calculations that the member states handed in. And it also could be the basis for the application of monitoring measures for national renovation roadmaps. So the conclusion on the optimization of technical building systems is that they are actually, according to the results of our study, very attractive, a big no-regret potential to actually, and this was the major target of the EPBD revision, accelerate the cost-effective renovation of existing buildings across Europe immediately. And technical building systems are an indispensable counterpart of the improvement of building envelopes for reaching a climate-neutral building stock. So that's the finish of my part, and now I hand over to Helge Schramm. Thank you very much.
Thanks a lot, Andreas, and excellent overview. But we have heard about a sleeping giant and huge energy saving potential, but how are concrete technical measures look like? So my storyline for today will be to take you on a journey around Europe to see how technical measures for optimizing the energy use of technical building systems are concretely look like. So to say, how to achieve the untapped energy saving potential. And as I'm sitting right now in our beautiful headquarters in Norfolk, I would like to start with a real case from Denmark. What you can see here on the first slide from my presentation is a single family house in Køge, and the family consists of 2 adults and 2 children. And they have been capable to save 38% on the energy bill with individual room temperature control. The single family house is a 200 square meter house built in 1985. And in 2011, the family decided to install electronic thermostats. The Danfoss Link electronic thermostats, which you can see on the right side, are connected with a central controller, and the entire installation takes place in half a day. So this is also good to know when we talk about something like no-brainers. That's not high sophisticated. Of course, it's advanced technology, but it's easy to implement. And in addition, with the Danfoss Link app, the family can control the heating from anywhere and adjust the heating system also to fit their daily schedule. So that means, for example, lower temperature when they are not at home, or maybe when the daily schedule change, maybe due to webinars. And the payback time of such solution is less than 3 years. If we move further to an example and real case from Poland, here we can see a multi-family building that has been capable to reduce the energy consumption by 16% due to temperature-controlled circulation. The building with 128 flats has 15 domestic hot water circulation risers and has been equipped with so-called multifunctional temperature control valves in 2003. And these thermostatic self-acting proportional valves, which you can see on the right side, provides thermostatic balancing of hot water systems within a specific temperature range, for example, from 35 to 60 degrees centigrade. And there are some additional technologies like capability to measure the temperature, and these valves are also designed to prevent unwanted tampering. But originally, the water distribution among the circulation risers was solved with manual balancing valves. And therefore overflow and high temperature was typical in the system, which means energy losses. And of course, this is something we would like to avoid. So after the renovation, the circulation became temperature control, and of course, this is what we would like to control. And the payback time of such an investment is less than 6 months. So actually, there's no reason to not invest in technologies and no regret or no-brainer technologies like this. What you can see always on the slides during our presenting is a link on the bottom where you can find further information about the case, because I cannot go in every technical detail, but you can always follow the link you will find on each page for further information. So if we move further, there's a case from Romania, and it's an office building at Floreasca Park, and they achieved 40% energy saving with an innovative heating and cooling system. In addition, this building was award-winning in 2014 as the best office building of the year at the Central and Eastern European Quality Award. How does the heating and cooling system look like? The heating and cooling system is based on a ground-coupled closed-loop heat pump system using geothermal energy of the Earth as a free energy source. The core technology within the system is the hydronic balancing, which is performed by almost 2,000 pressure-independent balancing valves. So within this building, 2,000 pressure-independent balancing valves, which you can see on the right side, are implemented. And the valves ensure accurate temperature control even at low flow rates. And why is this important? Considering different part loads, of course, the exact flow limitation of the valves at any load condition prevents excessive energy consumption. And considering this also allows the designer to have lower pump head constructions than traditional setups. That means also to minimize energy consumption. The investment in pressure-independent balancing and control valve provides intermittent control of energy distribution, and we have heard this from Andreas just before. When we talk about optimizing the energy of technical building system, then we are talking about optimizing the energy distribution, emission, and control. And here with the pressure-independent balancing and control valve, we have a solution with a payback time around 2.5 years. Further on, as the temperature is right now not really high in Denmark, let's travel to Italy. And what a surprise, even there, they need space heating in multifamily buildings. The multifamily house in Milano has been capable to reduce noise and reduce the energy consumption by 12% with automatic hydronic balancing. The interesting part here is that the project starts because tenants complain about noise caused by overflow, which result in turbulent flow in the risers. The 5 buildings constructed in 1965 have been equipped with automatic balancing valves in 2014. And the risers, as you can see on the right side, is controlled by 2 valves. The shut-off valve in the flow pipe and a differential pressure controller mounted in the return line. When we talk here about controller, we talk about self-acting control valve and not an electronic controller. The investment in this case has a payback time of 2.2 years, and due to the optimization in this specific case, 16,500 cubic meter of methane can be saved annually. And of course, this case also goes hand in hand and shows that energy efficiency is also linked to comfort, means less complaints about noise, and improved control, less need for commissioning. Further on, moving back north, a case from UK, and as you can see on the picture, no reason to be worried, means we could reduce the fan speed by installing variable speed drives. And you can see here VLT HVAC drives. The VLT is a brand name from Danfoss. By installing these drives to the air handling equipment, the hospital in Brighton has been capable to achieve 50% energy savings. This drives enables the hospital building management system to respond to changes in outside air temperature, duct pressure, or duct temperature. And of course, this provides versatility which is needed for the challenging requirements of the environment within a hospital. The energy figures have been recorded before and after the implementation of the variable speed drive, and they demonstrate the dramatic reduction in electricity consumption, around 533 kilowatt hours. When I started working this morning, I look into the energy figures of our 2 megawatt solar power plant next to our office headquarters in Nordburg, and during the time from January to April, we have produced 408,000 kilowatt hours. So might be due to the weather conditions, but overall it shows that energy efficiency is the first fuel when it comes to climate and energy targets. And of course, these savings are not a surprise because it's related to the affinity laws. Maybe you have all heard about this. So purely it means, for example, reducing motor speed is proportional to the flow, and pressure proportional to motor speed squared, and power proportional to motor speed cubed. This means reducing the speed by 50%, reduce the power consumption by 87.5%. And in this case, the reduction of 20% will result in 50% energy savings. Finally, back to Nordburg and to Denmark, and close to Nordburg in between Sonderborg and Denmark, a supermarket in Høje has reduced CO2 emission by 34% through heat recovery. The surplus heat from the refrigeration unit is used for space heating and domestic hot water. And in addition, the system is connected to the district heating network and provides heat to 16 homes in the neighborhood. Altogether, the owner of the supermarket saves 25,000 euros annually on gas. And this is also a good case to show the potential of combined technical measures. As you can see on the right side, the findings of the Ecofys study show a huge potential for energy saving by optimizing the technical building system within the supermarkets of around 16 to 49%. This is something what you can see in the fact sheets Andreas has mentioned. And taking a holistic approach, considering energy sources within the building, you can save even more by investing